If two massive cargo ships are cruising side by side in the open ocean, something strange happens. Even with their rudders perfectly straight, the ships will slowly, inevitably drift toward each other over the water until they nearly collide. You've likely experienced this exact same physics glitch in your own bathroom. You turn on a hot shower, and the curtain suddenly blows inward, clinging to your legs, even though the room is completely draft-free. We are wired to intuitively understand solid mechanics. If a physical object moves, we naturally assume something pushed it. But fluids, like air and water, operate by a different set of rules. They move objects by pulling them through invisible pressure gradients. In the 1700s, Swiss scientist Daniel Bernoulli mapped out exactly how this works. He discovered that a moving fluid behaves like a closed system, where energy is always being traded from one form to another. By defining this relationship, Bernoulli gave us a way to calculate these forces with precision. It allows us to manipulate fluid speed to generate the specific pressure changes needed to move heavy objects at will. Bernoulli's equation acts like a mechanical seesaw, balancing static pressure, kinetic energy, and potential energy. If height remains constant, this relationship is rigid. Speeding up a fluid forces its static pressure to drop immediately and proportionally. You can guarantee that speed increase simply by forcing the fluid through a narrow constriction. Because a fixed volume of fluid must get through a smaller opening in the same amount of time, it has no choice but to accelerate. The moment it accelerates, the pressure plummets. This is a physical lever we can pull to create suction simply by making a fluid move. Take a look at this vintage perfume atomizer. When you squeeze the pump, you force air rapidly through a highly constricted tube in the neck. According to Bernoulli's principle, that sudden spike in air velocity triggers a severe drop in pressure right at the nozzle. This creates a suction effect that pulls the liquid perfume up the tube and sprays it out as a mist. Athletes exploit the exact same physics to manipulate a ball's trajectory mid-flight. When a soccer player curves a free kick, they are creating a pressure imbalance with spin. This spinning sphere shows the ball dragging air. Spin adding to wind speed creates low pressure. On the opposite side, spin fighting airflow creates high pressure. This high-pressure air physically pushes the ball toward the low-pressure zone, curving its path. Whether you are applying a cosmetic mist or bending a free kick, you are using fluid velocity to gain direct control over physical objects. Which brings us back to that shower curtain. As water sprays from the shower head, it drags the surrounding air into motion. That moving air speeds up, its pressure drops, and the higher pressure air in the bathroom pushes the curtain inward toward you. This mechanic scales to massive proportions during a storm. When a tornado passes directly over a house, it essentially acts like a giant, high-velocity nozzle. Wind racing over the roof at 100 miles per hour causes the exterior pressure to plummet. Because the air inside the house is still at a normal, higher static pressure, it violently pushes the roof upward and off the structure. The math is identical regardless of the setting. The same pressure gradient that annoys you in the bathroom can tear buildings apart during a hurricane. But the most critical application of this formula is how we use it to make 400-ton aircraft defy gravity and stay in the sky. For years, popular science used a myth called equal transit time to explain flight, claiming that air particles splitting at the front of a wing must meet at the back simultaneously. They don't. In reality, wing camber and angle of attack force airflow to turn. Air curves and accelerates significantly over the top surface. Applying Bernoulli's seesaw, this massive velocity spike causes a massive pressure drop above the wing, creating an upward vacuum force called lift. This pressure differential works alongside Newton's third law. As the wing deflects air downward, the air provides an equal upward reaction, allowing for stable, controlled flight. From cargo ships drifting together at sea to jetliners cruising at 30,000 feet, every one of these movements is driven by the relationship between static and dynamic pressure. Bernoulli's equation is a specific application of energy conservation. It shows us that as air and water move through the world, they are constantly trading pressure for speed, ensuring the total energy within the system remains perfectly balanced.